We're going to talk about something new here, our last new topic of the quarter, or the year for some of you guys, and that's harvesting. Oftentimes when a resource manager like the Forest Service or the Division of Wildlife are managing a resource, they will harvest a certain portion, a certain number or a certain proportion of the resource, either for recreation in the case of hunting, or because they feel that it makes it more sustainable, because if they don't hunt them then there'll be disease and all that kind of stuff, or simply to make money in the case of lumber. Anyway, and that's called harvesting, and you can harvest either by a set amount or a proportion of the population. Anyway, but if you open the packet to page 214, take a second to do that, and you'll see a problem that has to do with elk population. And you can take a minute to read that. But the general idea is this. There are 200 elk currently, and they have an RMAX of 30 and a carrying capacity of 1,500. And when they and when we put this back in, when we write that equation, you can see here is my version of that, and there's my 30%, my RMAX, here and here, and here's my carrying capacity of 1,500, and then my P of n minus 1 squared, and my initial condition, P of 0 equals 200. Well, let's say that the wildlife managers wanted to harvest a certain amount each year, set amount. So let's say that each year they are going to issue 50 elk permits. Well, in order to change the difference equation, all we have to do is add that minus 50 on the end. So it's just like at a linear difference equation. You just stick that sucker right on the end, and you can see how it changes each year. So I've programmed all this into my spreadsheet here. So here in this first column is my my first difference equation there. And it looks essentially like this. I'll give you a second to look at that. And when I pull that down, you can see that value quickly approaches that 1,500 mark. This column is the 50 elk hunted, and you can see that the only difference is this minus 50 on the end there. And let's see what happens with that population. I pull that down to a similar range, and you'll notice that it no longer goes up to that 1,500 mark. It seems to level off somewhere just over 13,000 or 1,300. Let's look at the graph of these two functions and see what that looks like. And you can see this is our original difference equation, and this is our harvesting difference equation. You can see that it seems to level off a little bit lower, and it takes a little longer to get all the way up there. Okay. Now, if we wanted to find out exactly what that equilibrium value was, we could solve for that, and it's going to require just a little bit of algebra to get it set up. Now, remember, when we find equilibrium values, okay, we're essentially seeing when the new term is, let's do it this way, when the new term is equal to the old term. And so we call it all E. And then we got our minus 50 out here. Now, let's get rid of this other stuff just to get it out of the way. And let's see if we can solve this equation. So now, first of all, remember that whenever you'll see this is a quadratic equation because we have this e squared, right, which is exactly the same as, that. And we know that we need to have it equal to 0. So I'm going to subtract e from both sides. And I will get 0 equals, so my two common terms here are e to the first, so I'm going to end up with 0.3 e minus this number, which I'll figure that out in just a second, 0.3, because I probably want to have that be something that I can plug right in there. And all of a sudden I've got my e term, my a, and remember that all equations follow the ax squared, ax squared plus bx plus c. So in order to solve this, I've got to use the old quadratic formula because none of these are going to factor that well. Well, online, there's this magical tool called the quadratic formula calculator. So let's pull this off to the side and let's see what we can stick in here. So A is the, remember that my A is the term, okay, I'm going to do some calculation here, hold on. Right. Well, I'm sorry. This behaves a little bit differently than my last one, the other recording program. But anyway, so I turned 0.3 divided by 1500 into 0.002. I just divided those out so that I could have numbers. And then I can plug that in. So 0.002 goes here, 0.3 goes here, and negative 50 goes here. And I solve that quadratic equation. And negative, and that's negative. And you can see my actual solutions are, here are my two actual solutions. One is 190, and here's another one at 1309. Now that's the one that we were approaching. Now remember that equilibrium values can be can be stable or unstable. So this last one, when we graphed it, right? This is stable. We attract it. We go towards it, right? Now, let's see what happens when we go around 190. So I'm just going to change my starting amount, okay? Okay. I'm going to cancel that. So let's see what happens when I change my starting amount to 190. You'll notice that the population is actually decreasing here. So 190 is an unstable equilibrium value. In fact, which makes sense. So what this is saying is when the elk population gets below 190, it will crash. It'll all die. But when the population starts above 190, like at 200, then it keeps rising. Okay? Anyway, let's go back to this. Okay, so that was a fixed harvest. Okay, and we talked about how we could find the equilibrium value by plugging in E and then turning it into a quadratic equation and solving. And now let's look at the proportional harvest. So you can see in that second example there that they are harvesting 10%. Okay, so we'll kind of copy down this equation here. It's kind of my starting amount, right? And instead of just subtracting 50 like we did in the last time, they want to subtract 10%, okay? Which we can represent like this, P of times P of n minus 1, okay? Now you'll notice that these are like terms, okay? This term and this term. And so we can combine these. and change it to this. So just by combining those terms, all of a sudden I have a slightly different equation. So instead, this one's growing by 2%, or yeah, 20% per year because we subtracted that 10% over here. Okay, and we can go in and graph this equation too. So the only difference here is I actually left it over here as 0.1 d times d2. So there's my equation. You can pause it and look at that for a second. Okay. And I pull that down, and I get another. It seems like I'm approaching an equilibrium value there around 1,000. Yeah, looks like I'm approaching that. And let's graph all three of these and see what it looks like. All right, so you can see here's the original difference equation, just a regular logistic difference equation. Here is the proportional difference equation that levels off at 1,000, looks like. And here is the 50, the set amount. And so here are those three. Here are those three equations, graphed and all that. So you can see they all have different amounts. And once again, we could solve for this equilibrium value and make sure that it's 1,000. But that's kind of the idea. So set amount, proportional, original. I will share these documents with you as well, if that helps, so you can copy any equations and stuff. All right, thanks a lot. And then we'll do the homework problems tomorrow in class.